When you ask an AI to summarize a 50-page document or generate hundreds of lines of code, the speed makes it feel like you are talking to a single, brilliant brain. For lightweight everyday tasks, that illusion is actually true. Models like Google's Gemini Nano are built to run entirely on your local device, like a Pixel phone, processing quick suggestions without ever sending a byte of data to the cloud. If you want to run heavier data processing or train small AI models locally, you have to scale up to a high-end standalone processor. You're looking at hardware like Intel's HX series or the AMD Threadripper. These localized chips possess immense computational power. They can easily handle heavy 4K rendering or simulate complex digital environments entirely inside a single machine. But that localized power hits a hard ceiling when you scale up to the enterprise level. Imagine a platform like Google's Vertex AI, tasked with analyzing hundreds of thousands or even millions of documents every single month. Under that crushing volume of requests, even the most advanced single processor on the planet will choke, overheat, and crash. To build AI at an enterprise scale, you have to abandon the idea of one giant computer. Instead, you have to physically link tens of thousands of individual servers together into a massive, unified cluster. Once you spread an AI model across thousands of separate machines, the immediate bottleneck becomes communication. Those servers have to share massive amounts of data with each other instantly. This diagram shows the physical solution, Category 8 Ethernet. Inside, 4 twisted copper pairs are wrapped in dense shielding, blocking external electrical noise. This strictly protected cable pushes data at 40 gigabit speeds between servers, maxing out at a strict 30-meter physical constraint. That zero-latency, high-speed connection over short physical distances is what allows thousands of separate nodes to act together seamlessly as one giant computing unit. Even with the perfect physical connection, a logistical problem remains. If millions of users send queries at the exact same time, how do you prevent that massive hive of physically connected servers from being immediately overwhelmed? You put a traffic controller at the very front of the cluster. In enterprise networks, this is a load balancer, like the F5 Big IP. This diagram illustrates the virtual server and its virtual IP. This single public-facing address absorbs the impact, masking a hidden network of smaller machines. It continuously checks the capacity of every physical server, instantly routing traffic around busy or failing nodes to healthy back-end servers. Without the virtual IP orchestrating that intelligent, real-time traffic distribution, the physical hardware cluster would suffer localized bottlenecks and rapidly collapse under its own scale. An AI data center is a high-precision grid of silicon and copper, where every hardware component must act in perfect sync. Deploying a heavy enterprise workload, like running a custom Gemini model behind an API, requires every piece of this environment to harmonize perfectly to function. It relies on the raw math of specialized local processors, the extreme short-range physical architecture of Cat8 cabling, and the intelligent traffic orchestration of the load balancer. The modern AI experience, the magic of asking a complex question and getting an instant answer from what feels like a single brilliant brain, is an illusion. It is a carefully engineered reality maintained by massive physical infrastructure, working seamlessly in fractions of a millisecond.